Hello students. So next question is question number 6. Okay. So f is from closed interval -1 to 1 to a set of real numbers given by f of x equal to x upon x plus 2. Okay. Is 1 1. This is given 1 1. Okay. Find the inverse of the function f from -1 to 1 to range of f. Okay. And hint is also given, that is y belongs to range of f and y is equal to f of x, then x is to y upon 1 minus y. Okay. So it is given that it is 1 1. Okay. We have to show that it is given. It is 1 1. Okay. So let's start. So let's say x1, x2 belongs to domain f of x1 is equal to f of x2, x1 upon x1 minus 2 plus 2, x2 upon x2 plus 2. Okay. Cross multiplying, you will get x1, x2 plus 2x1, x1, x2 plus 2x2. Okay. This gets cancelled. So 2x1 equal to 2x2, which implies x1 is equal to x2. So this is 1 1. Okay. Now we have to prove whether it is onto or not. Now they have given that range of f, right? F is from -1 to 1 to range of f is onto. Range of f means full y set they have given. So that has to be onto. That is clear. Okay. Now 1 1 and onto. So the function is bijective, right? Function is bijective. So we can say that it is invertible. So inverse exists. Right? So if I take f of x equal to some y, f of x is x upon x plus 2 equal to y. So x is equal to xy plus 2y. So x is equal to 2y upon 1 minus y. Okay, so this becomes the inverse. That is, if I take this as some other this thing g of y, so 2y upon 1 minus y. Now we have to, this is our inverse function, that is f from, that is g is from -1 to 1 to range of f. Okay. And now we have to prove that this is, find the inverse of the function. Okay. Inverse exists or not, that also we have to prove. So from this to this, just a minute. This is our function from range of f to -1 to 1. Okay. Now we'll do G composite F and F composite G. Okay, as we have both the functions f and g, f is our x upon x plus 2, right? So starting with g composite f of x. Putting here x upon x plus 2 upon 1 minus x upon x plus 2. This is 2x upon x plus 2 upon x plus 2 minus x upon x plus 2. It gets cancelled. 2x upon 2, so we'll get x. So g composite f of x, we are getting x. Now we have to check for f composite g of y. 2y upon 1 minus y. Now we have to put this in this function. So 2y upon 1 minus y upon 2y 1 minus y plus 2. Upon 1 minus y cross multiplying 2 and 2y. So 2 gets cancelled, we will get y. Okay. So both we are getting identity. So this is the inverse. This is the inverse. Question 7. Consider f from R to R given by f of x for x plus 3. Show that f is invertible and find the inverse of f. So first you have to check whether it is 1 1 on 2 so that the inverse exists. Okay, then you have to find the inverse. So f is from R to R and it is defined as f of x equal to 4x plus 3. Okay, so let x1, x2 belongs to R. 4x1 plus 3 is equal to 4x2 plus 3. So x1 is equal to x2. So this is proved. Okay, 1 1 is proved. Now for on 2, say let y belongs to R such that f of x is equal to y. So 4x plus 3 is equal to y. So y minus 3, x is y minus 3 upon 4. Okay. Then we have to put this x in f of x. Y. So this is onto. Okay, 1 1 and onto is proved. So we can say that function is invertible, means f inverse exists. Okay, now we have to go for f inverse. We have to define g from R to R. F is our 4x plus 3 and g we have got y minus 3 upon 4. Okay, now we have to check for f composite g of y. So this is y and g composite f of x. Okay, so both we are getting identity. So f is invertible. Inverse of f is f exists. So f inverse of x is defined as g of y, which is y minus 3 upon 4. Okay. Next question, question 8. Consider f from r plus to 4 to infinity given by f of x equal to x square plus 4. Show that f is invertible with the inverse f inverse of f given by this. Okay, where r plus is the set of all non-negative numbers, real numbers. Okay, f is from invertible. So first thing you have to prove is 1, 1 and on 2. Okay. So let x1, x2 belongs to r plus. So f of x1 is equal to f of x2. Let so x1 square plus 4, x2 square plus 4. So x1 square is equal to x2 square. Now they have taken domain as the set of all positive numbers, right? So if you take x1 root of x2 plus or minus, negative numbers are not there. Only positive numbers are there. Okay, so f is 1, 1. So we'll get only the values x negative, all positive x values, not negative. Okay, so this is proved 1, 1. For on 2, you have to take some y belonging to codomain 4 to infinity. Okay, such that f of x is equal to y. F of x is our x square plus 4 to y minus 4. So x is root of y minus 4. Okay. And it is defined from 4 to infinity, right? So all the numbers which are greater than or equal to 4. So if I take here 4, it will be 0, 5, it will be 1. So no negative numbers are there. So this value x is going to be always greater than or equal to 0. Correct? And it has to be like this because our domain is defined to be a set of all non-negative real numbers. So this is true. So we can say that f is onto. You can put this value in your f of x and check. So you're getting y. Okay. So f is 1, 1. F is onto. So we can say that f is invertible. F inverse exists. So we can define a g from 4 to infinity to r plus. Okay. And g of y is our root of y minus 4. Now we have to check for G composite F and F composite G. This is Y. Okay, so this is getting Y and this is X. So both identity. So we can say that F inverse exists. F inverse is given by G of Y root of Y minus 4. Okay.